What is up, guys? Today we're going to be talking about a very important and very useful tool called Wireshark. Now, if you don't know about Wireshark, Wireshark is a packet capturing tool that you can use to capture incoming packets that your network interface or Wi-Fi card or Bluetooth card can see over the air, over the Ethernet wires, or you can also analyze packets. So we're going to be doing a little bit of both today. Wireshark does have some sample packets that you can analyze, look at, test your skills to see some stuff, and then also just to see what these packet captures should look like for different internet protocols and stuff like that. Wireshark did just have an update, so I just updated it, and we're going to show you guys how to download it, use it, and yeah, so let's get started. So the first thing you want to do is download it, obviously. There is a 64-bit and 32-bit installer. Pick the one you need for your system. Most you'll be running 64-bit. There's also Windows portable apps. I'm thinking Windows phones aren't a thing anymore. Maybe for like a 2-in-1 tablet or something. And then Mac OS. This is obviously the Intel ones. So if you're on a new Mac that just came out and it's running the new Apple Silicon, this isn't going to work. And then obviously source code so you can build it yourself. So I'm going to be grabbing the 64-bit installer. Click on that. Click yes. Click yes. Next. Noted. All of these are good. I mean, you don't need documentation, but none of this is like bloatware or anything that you're going to want to get rid of. So click next. I did unselect start menu and quick launch. I just want a desktop icon. And then we do want to associate trace files because chances are you're not going to associate a .cap file with anything else besides Wireshark. So we're going to click next. You can change your destination folder. I'm going to leave it on my C drive. That's fine. Click next. It's going to install npcap. This is for network packet capturing. And it's also going to install USB cap, which is for USB traffic. Also, USB wireless cards, I want to say. I think that is required. So it's going to run through, extract everything, install it, and it doesn't take very long. It looks like we are about done. Click next, finish, and then we're going to head on over. I did already download the files. I'll have the link to the sample packet captures so you guys can follow along or try some other ones that I didn't get to today. All right, so now that we have Wireshark installed, let us open it up, take a look, and see what we find. So we're going to double click Wireshark to open it. It's going to find us our local interfaces. It's also going to show you files that you've recently opened. I'm not really sure why it's showing me these files. In the past, I haven't really seen them. These are very old files from a couple of CTFs that I was doing. And then these are more recent files, and these are what we'll be looking at today. So down here, you're going to see your interfaces. So we have the Ethernet, that is our default one. And then Ethernet 4 is actually the same thing, more or less. So Ethernet, the default switch, actually conglomerates a couple of your devices together so you can see everything. And then Ethernet 4 is my local area network. There's some random ones, Bluetooth, Wi-Fi, some VMware network adapters that VMware just creates for you, even though you don't want them, and then loopback. So we are going to open up Ethernet 4. And then at the top up here, there is a lot of stuff going on. We're not really going to get into a lot of that. This is a very simple introduction to Wireshark. We're going to go over a little bit of protocols, destination, source, info, and then go over some files. And that's going to be about it for this video. So at the top here, there is one button that you will want to use. So if you scroll up, you can see that I am no longer following the flow of data. This is still going up because there is more stuff coming in. And if you ever want to go to the bottom and make sure you are up to date, click this little button and it says automatically scroll to the last packet during a live capture. So this is a great little button. It does flow very fast, especially if you're on a large network, or even if you are on a small network at night when no one is online besides me, I guess. I am definitely online. Anyway, so let's go up to the top. You can see there's a file. Can't really do much right now because we are in fact capturing. Edit. It's basically all of the normal stuff besides telephony. So telephony deals with voice over IP, SIP, LTE, all that fun phone talk stuff. So this is if you're dealing with a corporate system where they have voice over IP phones or SIP connections, or if you're dealing with phone towers. LTE is still a network protocol, so Wireshark can still mess around with it. So that's why they have all of this. Wireless, you have Bluetooth and you have WLAN, so that is WPA and wireless traffic. Tools and help. They do have a wiki and they do have sample captures. This is where I got the captures we're going to be looking at, and they do have their website. So let's take a look at a very simple one first. We're going to go to command prompt, and you can already see what I'm going to do because I forgot to clear it. So let's clear. Oh, it doesn't work on Windows. Dude, going between terminal on Linux and command prompt on Windows is disappointing sometimes. Anyway, let's just ping our router. So 192.168. I put a comma. Yikes. 168.1.1. And now before any of you get a panties in a bunch, these are all internal IP addresses. And if you know anything about networking, you know that these IP addresses don't really mean anything. And if you tried to attack 192.168.1.1, you would attack your own router. Or if your network is on 10.0.0.1 or 192.168.0.1, you would be sending packets into the ether, into oblivion. They would go nowhere. So let's hit enter here. And let's see what Wireshark is doing with this. So it is going much too fast for me to actually find it. Of course, my router did a broadcast right when I was trying to freaking do this. All right, so we have ICMP. I'm actually going to do a filter. So we're going to filter for ICMP, and we're going to see the entire ping request. So we can see each ping request and reply is all 74 bytes in length. That is the standard for Windows. On Linux, it is different. I believe it is 73 bytes in length. Why that is, I could not tell you. Actually, there is actually a little bit that I can tell you about that. Linux, so ping requests have no meaning. Whatever you ping to someone, they are going to send you that exact data back. You could put whatever you wanted in there. I'm pretty sure Linux puts the alphabet. It's like the alphabet a couple times. And then Windows, it was something completely different. I don't remember what it is. I went into it on a networking class years ago. But that is besides the point. That is very besides the point, getting off on a tangent here. So let's look at here. So this is the packet number. We can see these two are right next to each other. These two are right next to each other. These two are right next to each other, and these two are right next to each other. So the requests and the replies are very close together. And then the next ping request is a little bit behind. It takes a little bit longer to happen before the request. So they're grouped together based on their requests and replies. So you always see two of them together unless there is just a bunch of stuff happening. Because you can see they're actually within 0.001 of a second together, and then the other ones are within 0.01 of a second. So just that little tiny difference is what separates them by, 60 packets? That's crazy. So anyway, you have the time here. Now this is the time from the beginning of your packet capture. So we're at 200 seconds here. You have your source. So I'm sending it from .1.7, which is my Ethernet 3, which is my Asus motherboard's Ethernet thing. Ethernet thing. Ethernet controller. It's actually an external one. It's a PCI expansion slot. And then the destination is our router, which is 1.1. The info says it is a echo ping request. There's an ID, a sequence, a time to live, and the reply was in 4507 or whatever. And that is the packet number that is over here. So you can see the destination and source MAC addresses, the destination and source IP addresses, time to live, a bunch of information, and then the data is at the bottom. If you want to look, you can see the actual hex values, and then you can see what is converted into ASCII, and you can see I was correct. There is a alphabet all the way to HI, so they stop it at I, so it is high at the end. So I was a little bit wrong about that. I want to know what the Linux one is now. I'm very curious, but we won't get into that today. So that is a very simple packet capture. It was just an echo request with the ICMP protocol. But now let us stop this one. So let's actually get rid of our thing because we are still packet capturing here. If we hit enter and then go to bottom, it is still going. So we want to stop this packet capture. And now it'll let us open up file. We can save this packet capture, save as, export some stuff, print it, or we can open a new file. So let's open, and we're going to open our telnet raw.pcap. We're going to continue without saving because I don't have anything on this packet capture file that I want to save. And we're going to close all of these because I don't want to look at it at the moment. So as you can see, this is a simple telnet session between a client and a server. It is quite long. And if you look at the telnet data, you do see individual lines here. If you click on different things, you're going to see different lines of data. Some things are more important than others. Some things are more interesting than others. But a much easier way to do it than just clicking through each one is to right-click, follow the TCP stream. So this is going to show you all of the data, all unencoded, and here is the session. So this is almost what the user will see. The only thing is you're seeing client and server requests and replies. So if you see the login is doubled. Some of the user entered things are doubled. Some of this is doubled. But if you can tell, the password is not doubled. Now that is because the password is entered in, but it is not shown on screen. So that is why that is not doubled. Anything shown on screen by the server will become once. Anything shown on screen by the user is twice. That is why the username is doubled. So the username is fake. The password is user. We can see the banner of the server, and we can see he tried to type ls, but there was no files. And then he types ls-a, and that shows him all files, including hidden ones, because these are dot files. So they are technically hidden files. After he got done with that, he pinged yahoo.com. We can see that yahoo.com's IP address is 204.71.200.74 and 64 bytes, and 13 packets were transmitted, 11 packets received, and there was a 15% packet loss. The average round times, and then he typed in exit and the session was closed. When you do highlight things, it does take you to the packet that has it. So if I highlight user right here, it does take me to the telnet data that has the password and username and stuff like that. So that is kind of cool to note. But yeah, this is Telnet, and this is why you should not use Telnet, because if you use SSH, it would be encrypted and I would not be able to read this data. Now, this is why no one uses Telnet pretty much, And if you do, go rethink your life choices because there's probably something wrong. So we're going to close this and we're going to open up the next file. So open. Let's go with HTTP. This is a Gzip file. We're going to do a very similar thing. We're going to right click, follow TCP stream. Now this is a very simple GET request. If any of you have dealt with Burp Suite, which I'll be probably making a video about very soon, so get subscribed, hit that bell icon so you get notified when I do make that video. You can see the GET request for test/ethereal.html. The host is Cerebus. They're using Mozilla Firefox, and it is in English. The encoding is gzip, and it looks like it is an image, and it is encoded in PNG. Here's their cookie. It is a 200 OK, so the server is okay with that. The server is running Apache, and it's running Fedora Linux. Blah, 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 blah is encoded gzip again. Content length is 92 bytes, and here is the data. So this is the web page, and there's an image in it. But that's about all we get here. We can see IP addresses, MAC addresses, and how much data was going on, how long the packets took to go, and all of that jazz. So that was a pretty boring one. Let us proceed. We're going to open and let's go. We'll save the best for last. Let's go to TFTP. So this is trivial. Oh man, TCP stream is still enabled. All right, so trivial file transfer protocol. This is like FTP, but trivial. It's just simple. So we're going to right click it, follow the TCP stream. Ooh, you see that? It's not a TCP stream, it's a UDP stream. So let's click UDP stream and let's see what's going on here. That's not what we want. I don't want that. Let's go back. Go back and let's find something much better than that. Let's just click on a random file, follow UDP stream. Here we go. All right, so this is a very large text file. I actually forgot what it is. There's a name for it. There's something going on here. RFC 1350.txt. I don't know. It's like an academic thing, something internal that they're working on, blah, 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 blah. It's just a file that someone downloaded using TFTP. And so all of these packets together make up this file. And this is why we are seeing it when we follow the UDP stream, because 192.168.0.1 is sending it to 0.13, and someone captured it, and we're looking at it. So it looks like it's MIT. I was actually wearing my MIT sweatshirt a couple days ago. I do not go to MIT. So if you see me wearing college sweatshirts, you'll never know which one I actually go to because I have like 4 different college sweatshirts and I'm at one of them. But yeah, Solins at lcs.mit.edu. Cambridge. I don't know. There's a lot of stuff going on here, actually. I actually don't know what's going on. So let's close this out and let's go to the best for last. This is FTP. And let's get rid of the UDP stream filter and let's look at everything. So let's just right click on a UDP stream, follow UDP stream. We don't want that one. Let's follow a different one. Let's follow number 1. Do we see anything here? Nope. Number 2. Do we see anything here? What am I doing here? Follow UDP stream. Nope. Am I doing something wrong here? Follow TCP stream. There we go. So this is a GET request. It's very similar to HTTP. Partial content. Some web page content. So there's a lot going on in this packet capture. Let's find the actual FTP data here. Nutel, here we go. Nutella is a FTP server. Where is it? Nutella protocol. Nutella upload. So it is a protocol for FTP used to download and upload stuff. So let's go to TCP, and you can see that we can't really make much out of it. FTP is a little bit more secure than trivial file transfer protocol, so we're not going to be able to see much, but it is still not secure by any means. There is SFTP, which is secure file transfer protocol, which I would recommend to use over FTP almost always. So that's about it. That's Wireshark. So if you guys like this video, hit like, get subscribed, hit that bell icon. I am making content weekly. I upload Thursdays at 3 p.m. usually. If I do miss a week, please don't get mad. Sometimes schoolwork gets in the way of me and my YouTube career. So thank you guys, and as always, I'll see you guys all later.